I had 3 over z cubed. I'm asking if the
Yes.
inverse of that is 3 delta open bracket n minus 3 close bracket.
Yeah.
All right. And the
Wait
next,
a minute. Z cube, right? You said 3 over
yes,
Z cube?
yeah, 3 over z cubed.
Yeah, that's right.
On the next question, I know that 3 over z minus 1 is 3 u of n minus 1, but I'm asking could the answer also be 3 open bracket, 1 close bracket to the power n minus 1 u of n.
What was the second one?
3 open bracket, 1 close bracket.
Give me a second, wait. Give me a second. 3 what?
3 open bracket, 1 close bracket to the power n minus 1 u of n minus 1.
3 open bracket 1 to the power of n
Minus 1.
Yeah.
U of n minus 1. I'm asking, technically, is that answer also correct?
Correct for 3 over Z cube.
No. 3 over z minus 1.
Yes.
So that could have 2 possible answers.
2 that we know of. There might be more. I told you about this. I told you that digital signals quite often have more than one way to describe them.
All right, I got it. Thank you.
Today we want to talk about moving average filters. Moving average filters. And what's a moving average filter? An example is y of n equals 1/5.
I don't see a writing pad.
Excuse me?
I don't see a writing pad.
Okay. How about now?
Yes, I see it now.
Okay.
Thank you.
Okay, this is called a 5-term moving average filter. So our output only depends upon the present input and the 4 previous inputs. So what kind of filter is this? What kind of filter is this?
That's a FIR filter.
FIR filter, thank you very much. It's the FIR filter. So moving average filters are FIR filters. So the difference equation in y of n equals 1 over m sum n equals 0 to 4 to m minus 1 of x of n minus k. That's the succinct way of writing this. So what's the impulse response? What's the impulse response of this filter?
Wouldn't that be 1/5, open bracket, delta n,
Delta of n. I don't know why y'all don't pronounce the of.
delta of n plus delta, open bracket, n minus 1, plus delta n minus 2, close bracket, plus delta, open bracket, n minus 3, close bracket, plus delta, open bracket, n minus 4, close bracket.
Yeah. Yes. Why? Because with FIR filters, to get the impulse response, we simply change y to h and x to delta. Okay. I'll go to the next slide. What's h of z? What's the transfer function? What's the transfer function?
That's y is z over x is z.
Yes. That's what it is for every filter. What is it for this filter? What's h of z for this filter? This is for any filter. What is it for this filter?
Would the y is z be y of n and x is z be h of n?
Yeah, man. Yeah, man. How is it you don't know how to find the transfer function of a filter?
No, I know the concept.
No, apparently you don't. Because I'm asking for h of z and you haven't given it to me. Not just you, the whole class. So you can't tell me you know the concept if you can't give it to me.
All right, I see x is z. That'd be the z over z minus 1.
All right. Clearly, you don't understand
You
transfer
use the
function.
general rule. I mean, and you say the impulse response is the C inverse of H of Z.
Yes?
So
That's
that
the
means
truth. Go ahead.
every transport will be the Z transform of H of N.
The transform of h of n. And what is that? We have h of n. That's the last thing we have on the previous page.
We'll have to write it out.
Well, look at it and give it to me. me rewrite h of n. This apparently all having difficulty. I don't know why. That's the impulse response. So h of z, h of z, h of z is the z transform of this, which is 1, which is z to the negative 1, z to the negative 2, z to the negative 3, plus z to the negative 4. Because the z transform of delta of n is 1. And the z transform of delta of n minus 1 is z to the negative 1. How many poles are there? How many poles are there in this filter?
Five.
Where you get 5 from?
I looking at the bracket at the end at the 0 at the next.
And that's how we tell how many poles we have? Let me help you out here. That may. That's going. Isn't 1 the same thing as 2?
Yeah, you just put it in standard form.
Exactly. Exactly. And therefore, you see on the denominator, we have a 4th power. And 4th power means we have 4 poles. Where are all the poles? There are 4 poles. And by the way, 4 zeros as well. And 4 zeros.
You said the power.
Excuse me?
You said the power in the denominator determines the amount of poles. I didn't hear.
Yes, exactly what he said. And why is that news to you? I've been saying that since 320. The highest power determines how many poles you have. I don't know why that's news to you. We've got 4th power there, therefore there are 4 poles. Where are these poles located? Where are the poles located? Folks, you all don't know how to find poles? Is that what you're telling me? All right, answer this question, please. How do you find poles? How do you find poles in the system?
That's when you whatever in the denominator, you set it to 0.
All right. What do we have to denominator, Mr. Johnson?
D to the power 4.
D to the power 4 equals 0. You telling me you can't solve this? Is that you telling me you can't solve that equation? Mr. Johnson, is that what you're telling me? You can't solve that equation?
No. That's what I say.
That's exactly what you're saying. All right. If you can solve this equation, please go ahead and solve it.
No. All right. In order to get rid of the fourth power, you have to do a fourth root on both sides.
No, you don't have to. This here is equivalent to z times z times z times z equals 0. This z is 0, or this c is 0, or this c is 0, or this c is 0. There's your 4 answers. Z equals 0, z equals 0, z equals 0, z equals 0. So there are 4 poles. They're all located at the origin. What are the roots of the numerator? How are you going to find the roots of the numerator? How are you going to find the roots of the numerator?
You make it equal to 0.
You make the numerator equal 0. And how are you going to do that?
Put it right in octave.
Excuse me?
You can put it in octave.
You're going to put it in an octave. Thank you very much. I don't know what the rest of the people were worried about. I've said this many times. All right, so let me bring up octave. Y'all think I only use octave to show you in class. I use octave so you know how to use it when you need to use it. Apparently you don't think about it. You don't think about it because you don't want to learn electrical engineering. You just want to pass this course. So we do roots. Roots of what? Roots of what? What's the vector? What's the vector I want to find roots of?
All of them is 1.
All of what? All of how many are 1?
All in the numerator?
Yes. How many 1s do I need?
5.
1, 2, 3, 4, 5. Okay, close bracket. Close bracket. And there are my 4 roots. My 4 zeros. So let's do a pole zero diagram. So numerator is 1, 1, 2, 3, 4, 5. What was the denominator? What was the denominator?
That was z minus 4. I mean, z to the power 4.
So what is it? What's the vector?
That's 1.
1.
Followed by 4 zeros.
You've got the thing at the end, the semicolon.
Yeah, I got it. And so, what is it? Z plane. Z plane is the numerator first, and then denominator. What did I say? Oh, I have to load the package first. Okay. Package. I didn't realize I had to do that every time. Package load signal. There it is. All 4 roots right in the middle. And then your zeros are around the unit circle. Okay. So is this filter stable, unstable, or marginally stable? Is this filter stable, unstable, or marginally stable?
Stable.
Why is it stable? Well, how do you know it's stable?
All the points are in the circle.
As far in the circles as you get. As a matter of fact, there is no filter, no other filter is as stable as this stable. The magnitude of your root, the magnitude of your pole
That's 0, right?
is 0. So you far away from 1 as you can get. You can't get any further away from 1. So this filter is very stable. Very stable. All right. Let me know. Show you some of the uses. Okay. So that's the same fifth term FRL filter, moving average filter we're using. Right. This is now our input. This is the input on figure 514. That's the input we're putting into this moving average filter. Right. Notice that the second and third end value is higher than all the others. Now notice the output. And how do we get the output? We can use that filter command. Okay. The filter command I gave you. You got the A vector and the B vector. You got the input. So you can get the output. And the output is what you see here. So did you notice what happened? How's your output different from your input? Here's your output, here's your input. How does the output differ from the input?
I guess the output look a little more neat.
I don't know. I'm not sure what you mean by neat. I don't know what you mean by neat. What are you trying to say by neat?
The input like fluctuating and some higher and like go really high. Whereas with this one, they still have different levels, but
The word you're looking for is smooth out.
yes, sir.
The input is smooth out. You don't have the high highs and the low lows. Okay. So a moving average filter is a smoothing filter. If you want a signal smooth out, you'd use a moving average filter. Okay. Give you another example over the page in the textbook. See the top? Okay. You see the low? You see the two highs? You put it through a moving average filter, what happens? Well, it takes us a while to get up to the level we want, but then the peak is minimized, and this low is brought up. And then, of course, when the signal lands, it takes us a while to get back down to zero. So that's kind of stuff a moving average filter would do for you. Smooth out the peaks and the valleys. Let's look across the page here. I know that you all ever watch the stock market. Okay, up here in Figure 518, you see the variations, the variations from month to month. This is over a year. Okay. We put this top one into a moving average filter that filters over 3 days. Okay, and we got a smoother filter. That's in the middle. We got a smoother output waveform. We put it through a filter that smooths over 9 days. We get a really smooth waveform. And as you can see, the more you smooth, the more information you lose. The middle one is kind of a compromise between the two extremes. But it depends on what you want. If you want to see a clear picture of what your stocks are doing over the year, then the bottom one is probably the one you want to look at. You can clearly see it's kind of steady for a while, going up very slightly, and suddenly there's a drop. And then there's recovery. And then there's another drop over a longer period of time. So this is what moving average filters do for you. Okay. Now, here's a question we have not been able to answer yet. What's the frequency response of these filters? We haven't answered that question yet. Let's cast our minds back. Let's cast our minds back to 320. What do you do to find the frequency response of a filter? Let's go back to 320. What do you do to find the frequency response of an analog filter? How do I know an analog filter is low pass, high pass? What do I do to find out? Or band pass, or band stop? What do I do to find out? Wow, not one person can tell me? You're new to the job. Your boss says, go in and measure the frequency response of this filter I just invented. What are you gonna do? All right, Mr. Buchamp, Mr. Roll, you better answer this question because you're gonna have to do it in your project.
And you find the magnitude response, right?
And how do you do that? If I told you to do that, well, let's just talk about the lab first. If I told you to do that in the lab, what are you gonna do?
That's the output over the input.
That's the output what over the input what? Let me just draw what you just said. What's your input going to be? It's your filter. What's your input going to be?
That's X of S, right?
You're going to the lab. Your input's not going to be X of S. What's your input going to be?
My input is going to be the, call it now. That's the frequency of the thing of, I can't remember the word. Hold on. Hold on, man. He ain't clicking to me.
It ain't clicking because you truly don't understand it. I'm just going to call this filter. You're going to put in a sine wave. You're going to put in the sine wave. You're going to know the magnitude of that sine wave. And you're going to know the frequency of that sine wave. And we could call that 0 degrees. There ain't no harm in calling it 0 degrees. This is our input signal. Okay, and we're gonna get what? An output signal. And what's VR gonna be? What's VR gonna be?
Let me see. So.
Excuse me?
No, I was looking it over.
No, somebody said something. You put a sine wave in, what do you get on the output?
On output, you get a sinusoidal response. So
You get a sine wave also. Its amplitude is going to be B. And it's going to have an angle. So what is H of that frequency? I represent it as H of J. What's the frequency response of that frequency? What's the frequency response of that frequency?
that's VOC. Your VO, there'll be V over
Yeah.
input sine wave.
You're telling me this is B sine 2 pi ft plus theta over A sine 2 pi f? Is that what you're telling me? Because that's what I'm hearing you telling me.
Yeah.
And that's nonsense. When this bottom is zero, this top ain't zero. So this ratio is going to vary all over the place. This ratio is going to be infinite again, infinite. This ratio is useless. The problem is y'all still don't understand. Y'all still don't understand that transfer functions. This is a transfer function. Transfer functions are not worked with in the time domain. Both of these are time domains. In the lab, you measure in the time domain. That's what you do in the lab. You measure it in the time domain, but you don't work with it when you're trying to find transfer functions or frequency responses. You convert this to polar form. You convert this to a phasor, B theta. You convert the bottom to 0 degrees. And so H at that frequency is B over A, okay? Theta. So here's the magnitude of H, that's the magnitude of H, and here's the phase of H. That's the magnitude h. So even though you're in the lab, you're measuring time waveforms, time domain waveforms, you're not using the time domain waveforms. You're converting those time domain waveforms into phases. That's a lab situation. That's a lab situation. How do we do the theory? How do we find the transfer function? How do we find the frequency response at a given frequency? We find the transfer function first, 1 over s plus 1. What's that? What's that a transfer function of? What is this a transfer function of?
First order filter.
Yeah, but you can do better than that. What kind of filter? It is a first order filter.
First order low pass filter.
You can still do better than that.
Well,
You took 410, didn't you? You better say yes.
yeah, we took that.
There's one more thing that describes this. The first order Butterworth low pass filter. And not only is first order, it's also normalized. This is a normalized. What does normalized mean? This is a normalized first order Butterworth filter. What does normalized mean?
Means it have a cutoff frequency of, let me see.
Of 1
Yeah, 1 rods per second.
1 rod per second. I don't know why that person said 1 hay. No, frequency is not measured in hay. 1 rod per second. Normalized means omega c equals 1 rod per second. Now, how is it y'all don't remember that this is the Butterworth filter? I'm happy you remember there's a first order filter. That's happy, but that's they know that even the ELT 120 sometimes. Yes, in 120. I mentioned the fact that if there's only one capacitor or one S term, it's a first order filter. Here we are in our graduating class, and we don't remember this Butterworth. We eventually remember that it was low pass filter. That was good. None of us remember it as Butterworth. None of us remember it as normalized. Okay, but that ain't my point. My point is, you begin with a transfer function. How do you find the frequency response now? Because you see, if you all understood 320 really well, if you all understood it and remembered it, this course would be a breeze. Because so many things we do that are similar. How do we find a frequency response?
We have to find the magnitude of that.
We have to find the frequency response h of j omega equals 1 with j omega plus 1. That's the transfer function. This is the frequency response. See, it's telling you exactly how it's responding to frequency, to omega. Now we can find the magnitude of this. We can find the magnitude of this, which is 1 plus root squared. So this would be the magnitude response. Or we can find the angle of h, which is the angle of top minus the angle of bottom, which would be negative inverse tan of omega. And this would be the phase response. And we usually plot this on its own graph, and this on its own graph, the phase. The frequency response comes from the transfer function. The frequency response comes from the transfer function. Guess what? In digital filters, is the same thing. Okay. We start off with h of z, not h of s, h of z. Okay. It could be anything, but let's call it z minus 1 with z plus 1. Okay. Say, e.g. Then we form the frequency response. The frequency response. Now here's a new part. Here's a new part you don't know. To find the frequency response, we don't do S equals J omega. We do Z equals E to J omega. And you just have to accept by faith that's true. So the frequency response here will be H of, okay? And of course, it's not little omega, it's capital omega. Because capital omega is digital frequency. H of E to J capital omega, which is, in this case, E J omega minus 1 over E to J plus 1. This is the frequency response. This is how your filter behaves in the frequency domain. This is the frequency response. It's a transfer function. This is a transfer function. Right? This is a transfer function. But in respect to frequency. Therefore, this has a magnitude. I'm curious. Send me the magnitude of H. Let me see what y'all do. Let me see what y'all do with that.
Or the guard ready.
Yes?
I always was in class. I just had to switch devices just now. So I leave it off the next device. I give me another one.
Okay.
Dr. Cartwright, I can see the next page, please.
I haven't written the next page yet.
Sorry, I meant to say the page before this, page 4.
Back to the Future.
Thank you.
I wonder if I'm wasting my time here. All right, what's the key thing I need to know? Before I can find the magnitude, what do I need to know?
What is real and what is imaginary?
Yes. So what identity do I know? I need to know.
I didn't know that.
What identity do I need to know then? There's an identity I need to know so I can tell what is real and what is imaginary. What identity is that? The identity is e to the j omega is cosine omega plus j sine omega. So that's what the top becomes. Cosine omega plus j sine omega plus 1. So the top becomes, the real part becomes cosine omega plus 1 plus j sine omega. Sorry, minus 1. And the bottom one is cosine omega plus 1 plus j sine omega. Once you know that identity, then you should be able to find the magnitude. So find the magnitude of h for me now, please. And by this, by the way, this is identity e to j omega. I teach that in 120. I realize not all of you had me for 120. But this is identity. You don't know it now. You're going to need to know that from now on. Nobody? Nobody found the magnitude?
How you wanted us to send us through emailing?
You can do an email if it's easier. Okay, just heard something. Yeah, Mr. Chap, that's right. Mr. Johnson, do not write in pencil. How many times do I have to say this?
I didn't have no scrap paper, and I didn't mark up my book.
Well, don't send anything. Because what you said is nonsense. It amazes me that after all these years, students can't find the magnitude of something. That just amazes me. Pay attention, please. And the rule is so simple. The rule is so simple, and students cannot follow the rule. Mr. Johnson, what's the rule for finding the magnitude? Mr. Johnson, what's the rule for finding the magnitude?
I can't remember to that. I think some of the square root of the top minus the bottom, something like that.
Well, why you send me something if you can't remember what the rule is? Your time would have been better spent looking in your notes or even Googling. How do you find the magnitude of a complex number?
Yes, sir.
I think students don't realize there are rules for everything in electrical engineering. Well, not quite everything, but there are rules that must be followed. This is not gut feeling. There are rules that must be followed, and you must know those rules. Mr. Buchamp, what's the rule?
The rule
What's
is,
the,
if you want to find the magnitude, it's the square root of the real part squared plus the imaginary part squared.
Thank you very much. You first learned that in Math 168 and ELT 120. And here we are in the graduating class. What we have. Okay, so the magnitude of h is the square root of the top. The square root, real part. Is this a real part? Yes. Is this a real part? Yes. So the entire real part is the sum of those two. So we can square that. There's the imaginary part. And we're going to square that. And it's as simple as that. It's the square root. Square root of what? The real part. That's real. That's real. Therefore, the sum is real. This is the imaginary part. And we can simplify it somewhat. The top becomes the square root of cosine squared plus sine squared omega plus 2 cosine omega plus 1. Okay, and the bottom becomes, no, this is minus, sorry, minus. And the bottom becomes the top becomes, and the top, that's 1. Cosine squared plus sine squared is 1. So this is 2 minus 2 cosine omega square root over the bottom is the square root of 2 plus 2 cosine omega. And then if you know your identities, this is 4 sine squared, 4 sine squared omega over 2. If you know your identities, and the bottom is the square root of 4 cosine squared omega over 2. Okay. So we can remove square root signs, 2 sine omega over 2. Okay. And the bottom becomes 2 cosine omega over 2. Okay. So 2 cancels. And we're left with tan omega over 2. Tan omega over 2. The magnitude is tan omega over 2. But if you got as far as there, I was happy. I don't know who's sending me anything now because I asked them to pay attention. And of course, students don't listen. Let's see who this is. Oh, never mind. Nobody from this class. Okay. Now here's send me the phase now. Let me see what nonsense y'all give me. Send me the phase. Miss Buchamp, the rightmost part of your equation is right, but the middle part of your equation is not right. How can you have 1 inverse tan equal to 2 inverse tans? Oh, how is that possible? The middle equation shouldn't be there. I know that's a guide to you, but it's not mathematically correct.
Yeah, I just had it there as a guide. Sorry for that.
But you can't write things that are not mathematically correct. But the rightmost part of it is correct.
You don't need me to send it over, right?
No. I wonder if you could simplify it, though. There's the challenge.
Well, I hadn't graduated with marks a long time.
No. You can't be electrical engineer and say you're done with math. That's not possible.
I'll try it though.
Anybody else? All right, pay attention, please. What's my very first statement? Anybody else other than Mr. Buchamp? What's my first statement I write? All that time, the 320 and in 120.
I think it's the top minus the bottom for this one.
The top what minus the bottom what?
Phase at the top minus phase at the bottom.
Thank you very much. Angle of top minus angle of bottom. Okay. What's the angle of the top, Mr. Johnson? What's the angle of the top? What's the angle of a complex number, Mr. Johnson?
Oh boy.
Anybody, what's the angle of a complex number?
Zero?
Zero. So any complex number has got zero angle.
90 degrees.
Got 90 degrees. Any complex number, my friend, can have any angle between 0 and 360. Between 0 and 360. After that, it just starts repeating. The phase of a complex number is the inverse tan of the imaginary over the real. So that's the phase of the top. Minus the phase of the bottom. Minus the phase of the bottom, which again is what? The imaginary over the real. Okay, that's as far as Mr. Buchat went. I'm going to go further. Sine omega is in fact sine. Trying to get in. 2 sine omega over t, cosine omega over t. And the bottom is negative 2 sine squared omega over 2. So this 2 cancels that 2. All right. And this sine cancels one of these. So we left with cosine omega over 2 over minus sine omega over 2. All right. And then this one over here is minus inverse tan 2 sine omega over 2 cosine omega over 2. That's just an identity. That's an identity you should have learned in 168. And over the bottom is 2 sine cosine omega over 2 squared minus inverse tan. And this you could clean up. You could clean that up as well, but I won't go that far today. This 2 cancels that 2. So we have that sine omega over 2 over that cancels one of these, cosine omega t. And clearly this here simplifies to omega over 2. And this one simplifies here to omega over 2 plus pi over 2 plus or minus, I forget which, plus or minus pi over 2. So the final answer is going to be pi over 2 or negative pi over 2. It's going to be the final answer. Okay. Anyway, don't worry, don't freak out. I won't be asking you to give me this detail. If you get this far, I'm happy. Because you see, this here, you could put in a computer. All right. That's to jog your memory about magnitude and phase. And how much time we got? Not much. Okay. So just like then, let's get back now to moving average filters now. Remember, I just took a sidetrack just now. I just took a sidetrack to show you what you need to do to find the frequency response of a digital filter. You need the transfer function. Once you have the transfer function, you replace it by z equals e to the j omega. Z equals z equals e to j omega. In 320, it was s equals j omega. This is 320. This is digital. But you both begin with a transfer function. Okay. So now let me show you the magnitude response. Here's the magnitude response of that same 5-term moving average filter. There it is on the screen. We plot the magnitude response, and we get this magnitude response. So what kind of filter is this moving average filter then? What kind of filter is this?
What did you say about the plot?
What do you mean? What do I say about plot?
All right, let me ask you a different question. Was the previous the value is predicated on other values.
Boy, that's such a vague statement. I don't know what the hell you're talking about. Please ask a question I can answer. What are you trying to ask me? Or what values depend upon what values?
You did say something earlier, but I didn't hear you. But
And how long ago I said this?
about a minute ago, 2 minutes
So
ago.
I'm supposed to guess at what I said that you didn't hear.
I'll make an assumption it's a FIR filter, but
When I mentioned FI filter, that must be at least 10 minutes ago.
you did give a detail about this filter, and I was trying to, before I made that.
Mr. Johnson, do you understand what the figure on the screen is now?
That this would be the
impulse response.
smooth.
Excuse me, Mr. Johnson's talking. Please let him talk.
My bad. Apologies.
I don't know why he's so rude.
Bar 9. Sorry for that, Isha.
No problem. This would be the output after it gets smooth.
You talking nonsense. What does it say there on the y-axis? What is it measuring on the y-axis?
That looks to be the magnitude.
The magnitude of the filter. What's on the x-axis?
Digital
what?
Frequency, I believe.
Digital frequency. And the digital frequency goes from 0 to pi. Like I told you a long time ago, which you probably don't remember, the highest digital frequency you can have is pi. After pi, it just starts to repeat itself. So this is a plot of the frequency, the magnitude of the frequency response as a function of frequency. What has that got to do with smoothing in the time domain, Mr. Johnson? It has nothing to do with smoothing. I talked about smoothing 10 minutes ago, and that was in the time domain. That wasn't in the frequency domain. This is a plot of magnitude versus frequency. So this is telling you what kind of filter this is. What kind of filter is this?
Five-term moving average filter.
All right. That's a correct statement because that's where this plot came from, but it's not relevant to what I'm asking. In context of what I'm asking, is this a low pass filter, a high pass filter, a band pass filter, a band stop filter? What kind of filter is this?
That looks to be a low pass filter.
It's a low pass filter. And look at it. What's this cutoff frequency? What's this cutoff frequency?
I would assume like 0.25.
It is in fact. Okay, let me ask a question another way. How do we find the cutoff frequency from the graph? How do we find the cutoff frequency from the graph? What determines the cutoff frequency? When I ask you to read the cutoff frequency, what are you looking at? I don't know how y'all could have a whole course on filters in 410 and not know this. Anybody? When I look at this graph, how do I determine the cutoff frequency? I don't think you'll learn anything over the years. Y'all never can answer my questions when I ask them. Y'all should thank God I'm not interviewing you on your jobs for a prospective job. I used to hire people when I worked in industry. I ask you basic questions like this, and if you can't answer me, I show you the door. Because I don't care how many A's you got. You can't answer my simple questions, then I can't use you on my job. What makes the cutoff frequency the cutoff frequency?
Do we look at
Go ahead.
do we start looking at the part of the graph that's descending from one?
If you know the answer to this question, what makes the cutoff frequency the cutoff frequency? Why do we say, aha, there's the cutoff frequency? What makes us say that?
Sorry, I didn't hear that. I didn't hear the last part.
What makes the cutoff frequency the cutoff frequency? What makes us say, yes, that's the cutoff frequency? What makes us say that? The cutoff frequency is the frequency at which what happens.
The magnitude starts to descend.
The magnitude is how much?
That's when the magnitude starts to descend.
No. That's not the definition of cutoff frequency. Because if that's the case, where does this filter start to descend? I see a whole bunch of places where it's starting to descend. The cutoff frequency is a frequency at which the magnitude is 70% of its maximum value. In other words, in this case, the maximum value is 1, 70% is 0.7. It's a place where we point to 0.7 or another, what's 0.7 in dB? What's 0.7 in dB? Put 0.7 into your calculator and calculate how much dB that is. You all can't calculate dB now? What is 0.7 in dB?
It's -3.
-3 dB. What's the cutoff point? How many times did it say the cutoff point is 0.7 or -3 dB? How many times did they say that?
Probably 100.
How is it you don't know it when you need to know it? But how is it you can recognize I taught it to you? The cutoff frequency is the frequency at which the magnitude is 70% of its maximum value, or it's the frequency at which you're down by 3 dB. So since we don't have a dB scale on the y-axis, we have absolute scale. We look for the 70%. 70 that's 0.7. 0.7 go all the way across, hit the graph, and come down, and we have pi over m. The cutoff frequency is pi over m, where m is how many terms are in your filter, how many terms are in your moving average filter. In this case, pi over 5. The cutoff frequency is pi over 5. Which is 0.6283 radians. All these concepts from 320 and 410. There's nothing new in this class. Well, that's not quite true. There's very little new in this class. We have all these concepts. We have all these definitions, which we don't know. We'll have to end there for today, but we're not done. We're not done with moving average filters and their frequency response. We'll continue this next class. Have a good day.
You do, Dr. Carter.